Singularity. You're watching Singularity One-on-One, and my name is Nicola, aka Socrates. Singularity One-on-One is a regular podcast feature of Singularity weblog, where you can go and listen to it or download it in full. You can help me make this show better in one of several ways. You can simply go to iTunes and write a brief review. You can click the like button on YouTube. You can leave a comment on the blog or on YouTube, or you can simply make a donation. Today, my guest on the show is Dr. George Church. Dr. Church is a world-renowned geneticist, a professor at Harvard University, as well as the author of a fantastic book on synthetic biology called Regenesis: How Synthetic Biology Will Reinvent Nature and Ourselves. So, without further ado, let me welcome Dr. Church. It's very nice to have you on the show.
Oh, thank you very much. It's great to be here.
Fantastic. So, George, would you mind sharing with us, how did you become a geneticist and why?
Well, I really probably consider myself more an interdisciplinary and technologist than a geneticist, but certainly I have been interested in anything that was the intersection of math, computers, and biology. And one of the first of those was, for me, was crystallography. And the kind of crystallography I did happened to be nucleic acid crystallography, and that led pretty swiftly to molecular biology and genetics.
Wow. And for those who are not familiar with the term, what is crystallography?
It's really the use of three-dimensional crystals for studying the atomic coordinates, the atomic positioning of the molecules, in particular proteins and nucleic acids. Mm-hmm. So that's what I did when I started my scientific career.
And why did you find that to be so interesting and inspiring for you?
Well, it was actually one of the few fields of science, and certainly of biology, that had a deep need for and use of mathematics and computers. Because up to that point, there were relatively few fields that used those, and I love that particular application. Also, I just like three-dimensional objects. They're very real to me, and back then, most of the crystallography was done with a life-size, a human-sized model of a molecule. It was typically how you interacted with it, which was quite. Mm-hmm. And it was an engineering field. Certainly, there's a lot of engineering involved, and I like that too.
So you said that you consider yourself primarily an interdisciplinarian and technologist. So is that sort of the approach, that you're kind of bringing the technological, the engineering, the sort of computer view into biology and genetics?
Absolutely. We also try to reverse the flow, where we bring biology into engineering as well. And
do you feel there's any pushback or any friction?
No, actually, usually the biologists welcome anything that will make their life easier, less expensive, higher throughput, higher quality. All of that is something that the average biologist doesn't want to mess around with. It's a distraction, so they're happy when occasionally somebody will do it for them.
Mm-hmm. Now, I spent 10 weeks at Singularity University at NASA Ames campus a couple of years ago, and many of the people there were saying that just like in the late 70s and early 80s, many people were starting computer companies. Nowadays, in their garages or their father's garages, nowadays many people are starting synthetic biology companies. Do you think that there's a sort of a parallel biogenetical or synthetic biology revolution that is in many ways similar to the computer revolution?
I think it is, or maybe more broadly, the electronics revolution, in that electronics can be used for a variety of things which are not computing. Synthetic biology represents one way of manufacturing, and it's certainly an information science. There's a lot of digital electronics was about information science. It's possible that biology will be able to manufacture just about anything. That's not proven, but it's certainly the things that it can already manufacture are subject to revolution such as we've never seen in electronics even, which is, cost reduction of the factors of 10 in a year, rather than the usual 1.5-fold that we expect of the other revolution, the electronics revolution.
Mm-hmm. So you just mentioned that synthetic biology is actually beating Moore's law by a factor of 1.5 times?
No, by a factor of 6-fold. So it's Moore's law is about 1.5-fold multiplier per year, and I would say genomics technology, reading and writing DNA, especially reading, but also writing, is in the 6 to 10-fold per year range.
That's absolutely flabbergasting. That rate of change is I think it's entirely unparalleled in the history of science, perhaps, and humanity in general. Would you not agree?
I don't know of too many examples. I mean, you can get sort of short sprints, where typically characterized by having some infrastructure in place that's underutilized, and then a protocol that enables it. So, for example, the growth of the World Wide Web was quite fast in 1983, mainly because the internet was already deployed, and all you needed was a little protocol like HTTP, and then it spread. So, but I think with the exception of those things, which weren't really didn't require new nuts and bolts, fabrication technology, was just a protocol. With the exception of that, I would say yes, it's without precedent.
George, before we sort of dive into the meat of the matter here, I want to ask you a couple of other general questions pertaining to you. I might want to precede that by saying that, the reason why I'm asking those kind of personal questions is because I'm not only interested in what you're doing, but in why you're doing it and the story behind it, and to get a general better idea of who you are and what you're all about, what makes you tick, if you will. So let me just ask you out of curiosity, what is your take on religion? Are you religious in any way? And to sort of help you along, let me just share with you first that I'm 100% atheist.
Okay. So I was brought up, my grandparents were Catholic, Protestant, and Jewish. And so I got a lot of exposure to comparative religions, and then learned of Muslim and Buddhist during high school. And I would say that I'm probably more on the faith end of the spectrum than most of my colleagues. I'm not an atheist, but I don't put it in people's face one way or the other. I think it's something that it's certainly, faith is something that's hugely influenced the world, and that can't be denied scientifically. And also, there are many different aspects of faith, many different definitions and components, and even the strongest atheists have faith in something, faith that what they're doing is worthwhile, things like that.
Yeah, I agree entirely with you, but let me push you a little bit further more than here to identify that faith, if you could, that you meant. Because you mentioned that incredible mixture, if you will, between Judaism, Christianity, and did you say Protestantism?
Catholic and Protestant, Lutheran, yeah.
And then Judaism too.
Right.
So, yeah. And also you've mentioned Buddhism, and so which one of those religions is the one that you have the biggest sympathies?
I think they have a lot in common, actually, and I think that's what they have in common, which is the thing that holds so much attraction to people all over the world.
Because you see, for example, me, I always would say that I'm an atheist, but I just love Buddhism personally. Buddhism is one of those religions, especially Japanese Zen Buddhism. It's always been absolutely fascinating to me. And it goes a lot further beyond, I think, religion. It's a philosophy. It's a way of living. It's absolutely amazing in my view. So I have the highest respect for Buddhism, for example.
Yeah. I mean, there's no doubt that many of these religions have a secular component and a philosophical component that inspires people.
Mm-hmm.
When I was growing up, one of the most intellectual things I had every week was not my classes. It was the sermon of the pastor.
Wow.
He really was a very intelligent person, and providing a grounding for people. Sometimes in order to do well, to contribute to the community, to do altruistic acts, sometimes in many cultures requires, and for many individuals requires something bigger than themselves, some kind of community.
Mm-hmm.
Religions provide that a little bit better than any atheist organization I know of.
How about philosophy? I think that, as Schopenhauer said, Christianity, for example, is Platonism for the masses. Basically, most of the Christian ideas trickled down from the ancient Greeks and were put into, the Bible, the New Testament in particular. So I personally find inspiration by the ancient Greeks myself. I mean, that's because I have strong sympathies to philosophy, ancient Greek and Roman in particular.
Yeah, I don't claim to be an expert on any of these topics, but I think there's some ancient things that are quite interesting, and there's some new wrinkles as well. Some new, maybe not fundamentals, but just like in science, some new things that come up that are, some of them stimulated by scientific discoveries or inventions.
Mm-hmm. Okay, so let me move on here with another question. Is it true that just like Sir Richard Branson, you were dyslexic as a child?
Yeah, I'm mutant in many regards, but yeah, I have dyslexia and narcolepsy. I'm still not a particularly good reader.
Mm-hmm. Wow, that's absolutely incredible. That's absolutely incredible. By the way, since you mentioned that you are a mutant, I've seen a couple of interviews with you, and I want to share one area that we are the same mutants on. It seems both of us are genetically predisposed to have very high cholesterol.
Yes.
So I want to ask you, because I'm currently testing a bunch of experiments on that topic, and I want to ask you, how did you confront that sort of poor genetic lottery, if I can call it that way, of having high cholesterol?
I was actually in a guinea pig in a diet study when I was a teenager at MIT one summer, and my study was actually on leucine, but the study next to me was on hypercholesterolemia, and that was the first time I'd ever heard of it, and I had never been tested. And then later I found out my father had a problem with it. He had a triple bypass, and eventually it led me to statins.
So you're taking statins. Because the reason why I ask you is because I think I heard somewhere that you are a vegan.
That's correct.
And, yeah, go ahead.
So you need both, in my opinion. Statins prevent you from producing the cholesterol, and then the vegan diet prevents you from bringing cholesterol in from the outside. And I've tried both back and forth, and it seems like I need both to get it down.
Mm-hmm. Yeah, because I've been currently doing this sort of experiment. The whole month of January, I went about 90% vegan and maybe 10% vegetarian. This month, I'm going to go low-fat, February, and then in March, I'm going to go paleo, and at the end of each of those months, I do a cholesterol test, and then I will compare the readings between the 3 months after 30 days on each of those diets, and kind of try and come out, with a conclusion about which one responds best for me.
Yeah, I think that's a key point. Many diet books are written as if one size fits all. I mean, it's funny, we talk a lot about personalized medicine, precision medicine, but for some reason we still buy all these generic diet books. And there's no doubt that there are some, like the Atkins diet is not for everyone. I mean, there's some people have a ketosis response to it because of the the requirement for high metabolism of lipids and ketogenic amino acids. So, I think it's very important to figure out what diet works for you as rigorously as possible.
Do you think that we should be having a test, a genetic test that we can do anytime soon that can help us sort of make that decision whether we would be best on paleo or vegan or low fat or any of these?
Well, I think it's already the case that everybody should have their genome sequenced. It's affordable. It's affordable to a large fraction of people with healthcare, and it does tell you things like that. I mean, for example, there's some people that shouldn't eat fava beans. There are a lot of people that it's not as simple as paleo versus Atkins. It's specific things that you shouldn't eat because of enzyme deficiencies and so I think that you should have your genome analyzed, but you should also analyze the chemistry of your body as well, how it actually plays out. So the genome's fairly predictive for certain things, but it helps to get a reality check that goes beyond that you can integrate. I mean, basically, you shouldn't be using the genome in isolation, but use it together with other things.
Yeah, that's why I'm doing the cholesterol test at the end of each 30 days that I'm experimenting with those foods. But speaking of tests, I maybe 2 years ago or maybe even 3 years ago, I did the 23andMe phenotype DNA testing. So I wanted to ask you, what do you think of that? I mean, obviously it's not a full genome as you mentioned. So what would you want to say about that?
Well, so first of all, I'm an advisor to 23andMe since before they even started, as I am for other companies, and I think it's a terrific cohort that they're building up, and the addition of research to their portfolio was brilliant as well. I think they, as much as anybody, would love to be able to offer their clients full genome sequencing. They experimented with exome sequencing for a while, which is just the coding parts of the genome, and I think that's no longer available for now. But there's no doubt that once their current price is $99,
yes,
once full genome sequencing is $99, they will almost certainly offer it, maybe even before then.
And what's the current cost of a full genome sequencing?
So in a bulk price, it's less than $2,000. So there are at least two companies that are not, as far as I know, not losing money at $2,000.
Wow, that's absolutely amazing. And what's the factor of cost shrinking of that cost? That's not the sixfold that you mentioned before, that right?
6 to 10-fold per year is the record for DNA sequencing since about 2005, when we and others published the first examples of next generation sequencing.
So does that mean that a year from now we can expect the $400 tests for full genome?
So it's actually been fairly flat since 2010. It's dropped maybe from 4,000 in 2010 to about 2,000 late last year. Mm-hmm. So I don't know what it's going to do this year. I mean, I think the next big breakthrough is probably going to be in nanopores, and that hopefully that will be within a year or so. But it could be relatively flat for a while until that next technology comes in.
So perhaps that incredible rate of shrinking the cost is coming to an end, or has come to an end.
A plateau doesn't mean an end. It just means that waiting for the next technology. I mean, there have been many different plateaus. I mean, before Sanger, there were sequencing methods, and after Sanger slab gels, there was capillaries. After that, there was next gen for solid. And there's a whole series of these temporary plateaus, but I think I wouldn't be surprised if we get below well below $100 genome in the near future.
Near future meaning 5 years, 10 years?
Yeah.
5 years? Yeah. And you mentioned that perhaps one of the ways of going to the future would be nanopore. So I read a New York Times article probably, I don't know, a year ago about the company planning to introduce to market what they called the first USB DNA sequencer. I think it was called the Oxford Nanopore USB DNA sequencer. Have you heard of that?
Right, the Minion. So we had the first patent on nanopores, and we meaning Harvard licensed it to First Agilent and then Oxford Nanopore, and they had a demonstration. I think to some extent all the nanopore companies are in the range where they could be portable, battery operated, handheld. I mean, that's what's attractive about the technology. So whether it's Napsis or Genia or IBM, and there are a number of different companies in this field.
Mm-hmm. So that the future is obviously either going through, the laptop, the USB connector of your laptop, or through your handheld smartphone and things like that.
Right. I mean, there is the possibility exists that because it's basically an integrated circuit with a very minimal fluidics. It doesn't have the big fluidics that all the current systems have, where you have to do cycles of washing and so forth. This is something where you just put in a droplet and it sort of uses molecular self-assembly to do the right thing. Mm-hmm. And I think that's intrinsically small, low energy cost. It's something you could wear. It could be do 7/24 monitoring of your environment, mm-hmm. or of your saliva. It really could become a very useful adjunct for precision medicine.
Mm-hmm. So let me move on our conversation to your fantastic book here that I've been reading for a while. And it took me some time to get through it, even though, it's not the biggest book that I've read, but because it's, biology and genetics are kind of not my field. So it took me a while to get through it. So let me start you by asking you this for the sort of the people like me who are not familiar with the term, perhaps. What is synthetic biology all about?
Well, synthetic biology is trying to establish a molecular biology form of engineering. So genetic engineering had some of that component to it, but genetic engineering was never really didn't originate from an engineering background. It originated from a biology background, and this is to try to compensate for that. So in engineering, you might have computer-aided design, hierarchical abstraction, where you can take parts, put them together, and make a more complicated part. You have specification sheets. You have systems analysis. You have safety engineering. It's an important point. So all of these things were somewhat represented in a rudimentary state in genetic engineering, but now they're more formalized in it. And you can think of it in the same sense that genomics is studying all the genes at once, and synthetic biology is kind of engineering all the genes at once.
Mm-hmm. Mm-hmm. Just sort of to give more power to your words, perhaps I can read a short passage from page 4 here, where you say, just as computers were universal machines in the sense that given the appropriate programming, they could simulate the activities of any other machine, so biological organisms approached the condition of being universal constructors in the sense that with appropriate changes to their genetic programming, they could be made to produce practically any imaginable artifact.
Right.
And then
I think I agree.
I hope so.
Yeah.
I hope so. So what are the limitations to that way of thinking? I mean, that's really groundbreaking. But it's so groundbreaking that, people have called it sometimes the most dangerous idea, or among the most dangerous ideas.
Mm-hmm. Well, danger is everywhere. And to some extent, inactivity is one of the most dangerous ideas ever, is complacency and assuming things will be fine if we do nothing. We have a planet with an unprecedented number of people on it, all of whom want the wealth of the most wealthy people, which is a very consumptive attitude. So we have a crisis that requires constant reflection on danger. Danger and safety and security are some of the things that my lab does research on. So I don't know if this is the most dangerous idea. It may also be the best way of ensuring security, safety, and progress. But I think the main thing is we need to have attention to it. We need to be not just make knee-jerk responses where we say, "Oh, this is obviously good since it's new," like plastics or electronics were obviously good. I think that was naive, and nor should we say it's obviously bad because it's new. It requires thoughtful consideration of all the risks and benefits, including risks and benefits that aren't obvious immediately. It's like play the chess game as many moves forward as we can in order to assess the risks and benefits.
Now, to be more specific and more accurate, when Francis Fukuyama said that it's the most dangerous idea, he was speaking more specifically about transhumanism. But what, in your view, is the relationship between sort of transhumanism and synthetic biology?
Well, I think, if transhumanism is defined as going beyond our natural state, which is our tribal state, pre-industrial, we're well transhuman. That is to say, we have electronics highly integrated into our body effectively. There are many modern people who cannot be separated from their computer, cell phone. Their ways of communicating with other people is defined in that way. So, to that extent, our cars, our heating, housing, our food manufacture, all these things are very far from natural. And synthetic biology is just one new tool. What distinguishes it is that it's our first really atomically precise tool. It's the first nanotechnology that really works, and it gives us principal control over any material at any degree of resolution. And because it is, in a certain sense, it represents biology which is dirt cheap, literally. I mean, there are many biological amazing structures which are produced at scale, like trees, for example, that are in a certain sense atomically precise and self-replicating and free as long as you have sunlight.
Now, you've mentioned that in contrast to many of your colleagues, you're more on the side of faith. So do you find guiding principles or ethical principles stemming from your faith that would sort of guide you or tell you what you should or you shouldn't do, or how far you should go and how far you shouldn't go?
I think what's interesting about so some scientists will say science doesn't address the shoulds; it just addresses what can be done physically. But in a way, there are some shoulds that even science addresses. So, for example, there's what is likely to happen. In other words, if you look at a technology curve, you can observe, you can extrapolate. If you look at the historical precedents, you can see that most technologies that have been banned, and most radical technologies have been banned at some point or another. Kevin Kelly has documented this.
Yeah.
The length of time they're banned is shortening as time goes on, so that we're getting better at making them safer, adjusting to them, integrating them with other ways of thinking and other technologies so that they're socially acceptable. So those are really, those fall into what's normally the category is should. If you say something shouldn't happen and nevertheless it does happen, what does that mean? Does that mean that we should go back? In other words, if we're upset with the fact that we have that our crops, produce, runoff, fertilizer runoff. Does that mean we should go back to the pre-industrial way of raising food? That would probably result in 3 billion people starving. So that's not a very good should.
Mm-hmm. One of the most interesting ideas, and perhaps the most powerful way that synthetic biology can improve the human condition and alleviate suffering, make us perhaps all the way to absolutely immune to viruses, is the idea of creating mirror humans or mirror organisms. Would you mind telling us a little bit more about what do you mean by the term mirror organisms and mirror humans?
Well, in the book, I described two strategies that, in abstract, could make a cell resistant to all viruses. One, the easier one, the one that's closer at hand, and hopefully will happen in the next year or so, is changing the genetic code. So all viruses share a need for a common genetic code provided by the host. Mm-hmm. The idea of a mirror cell is that if you could flip so if you have just a cluster of atoms that are asymmetric, you can make another cluster that has the same atoms and the same distances, but are related by a mirror image. In other words, you hold it up to the mirror, the mirror image of one molecule will look like the other molecule, and those are chemically distinct. They have many predictable properties. They have from the first one. So if you know the properties of the one, you'll know the properties of its mirror image with high precision. But since most enzymes, most catalysts in a cell, in a human body or in a microorganism, have this handedness to them, they don't recognize the wrong hand, even though it's chemically predictable. And so that means almost every enzyme, the enzymes that degrade proteins and nucleic acids and so forth, all the components of your body, don't work on the mirror image. Mm-hmm. So that means if you made a mirror image cell, it would not only be resistant to viruses, but it would be resistant to enzymes, to digestion, to all sorts of predators and parasites as well as viruses.
Now, you mentioned that the easier way would be just to change the genetic code, and as you just said, you're hoping that this would happen within the next year or so.
Right.
How about the harder way of creating mirror organism? What's the timeline in your view on that?
Well, the milestones will be first creating a protein synthetic machinery, the ribosome, which will handle normal messenger RNA and make it into mirror proteins. This is one way. In principle, you could do it all chemically, or you could do it biochemically. We're trying both. Then the next step, once you have a way of producing lots of large proteins with high fidelity, but in the mirror form, then you can use those now to make copies of themselves, mirror proteins, mirror RNAs, making copies of themselves, and then encapsulate that into a lipid membrane, and then move it closer and closer to a mirror form of an existing cell. Now, the prerequisite for that that's really missing right now, we know how to make mirror copies of protein, peptides and nucleic acid, oligonucleotides. What we don't know how is how to get a cell to replicate from parts. We know how to change a cell so that it has a new genome, but we don't know how to, if we take it completely apart and put it back together without the help of a existing cell, that hasn't been done yet. Mm-hmm. And that's a little unpredictable when it could happen. But my guess is sort of 5 years is just a long time these days. And so 5 years was nothing. But in 5 years we've basically brought down the cost of some genomics by 1 millionfold. So I don't think it's out of the question that we should be able to get a replicating system from simple parts.
Mm-hmm. George, you mentioned you have many other interesting terms and topics in your book, and I'd recommend the book to any members of our audience today. Ideas like living software, why you call DNA the oldest text, and all of that, and many, many other precious ideas that I think would enrich anyone who reads the book. But let me move on here and ask you, what do you think of patenting living organisms? Is the patenting system that we have today, in other words, progressive and ensuring progress, or is it preventing it?
Well, it's a little complicated to say because it's hard to do the control where we have a system without patents. But what people sometimes forget to say in these discussions is the alternative to patents for any system, whether it's physics, chemistry, or biology, is not having everything free and open and easy to exchange. It's having trade secrets. So the whole point of patents is to entice people to tell their trade secrets to the world by giving them a limited temporary monopoly. So if I were to mess around with the patent system, it probably would not be to get rid of it completely, because that would result in more trade secret and more difficulty sharing. You might tweak the amount of time the monopoly lasts or something like that. But, I actually think it's not broken. I think the patent system works for physics, chemistry, and biology pretty well. What you need to do is to just make sure that the two criteria of being non-obvious and useful are met. Because if people are getting patents for things that are either obvious or not useful, then that complicates the.
You're talking here mainly from the point of view of innovation, though, and creating sort of technological progress, and the way the system is structured right now, it's very economic in its foundation. But let me ask you from an ethical point of view, would that change anything that, in chemistry, you may be talking about certain kind of a compound, but in biology, and especially synthetic biology, you're talking about living organisms, and perhaps eventually you might even start talking about sentient living organisms. Would that change things?
Well, I think, there's two components here, whether you want to invent at all, and then if you invent them, whether you want to reimburse the inventor for the invention. Do you want to encourage the inventor to continue to invent, to essentially pay for the innovation? I think that, right. So I think that, if they do produce something that's valuable to society, that's ethical in the sense that it saves lives, that it reduces, that it increases the chances our species will survive, improves the quality of life, then they should be reimbursed and encouraged to do it again. So I think that from that standpoint, whatever they invented should be encouraged. Now, is there an ethical problem with the invention when it's aimed at improving the quality of life?
If it comes, for example, at the price of suffering of that organism, let's say you create living sentient organisms for organ donors or for cloning, right? And then you basically destroy them after that because they are your own property. You've patented their creation. You're God for them. You give birth to them, you grow them, and then you kill them to alleviate suffering in what you would call the real human beings in society. Wouldn't that be creating suffering at the same time for those organisms?
Yeah, I think that would probably not, that probably will not make it into research and the marketplace, not because of a patent issue, but because of the ethics. So we have regulations, not just the EPA and the FDA, but we have regulations on, animal and human research. And I think there's almost always an alternative. That's the beauty of innovation, is you're not forced to do things the unethical way. There's all kinds of alternatives. And so as long as society continues to pass laws and discuss, so for example, for organ, I think that the more humane way would be to grow the organ, either print it or grow it a laboratory without nervous system.
Mm-hmm.
If you need a liver, you grow the liver rather than growing an entire being.
Mm-hmm.
So I think that's entirely feasible, and it may even be the most cost-effective way as well as the most ethical way. I don't think there's necessarily a trade-off there.
Mm-hmm. Now, if we go beyond the patenting system, let me ask you, what's your view, and is there any connection between the personal genome project that you were involved in and open source genomics, for example? What's your view on open sourcing much of the research there?
Right. So we're arguably one of the most open laboratories, in part because of the personal genome project. It as far as I know, it's the only open access data source for genomes, traits, and environments and their connection between them. For human beings, connecting genomes and traits usually means that it's either in a proprietary database where you can only get access if you pay a lot, or it's in a government plus industry database, which is also closed, so the average citizen can't get access to it, and very often it's not internationally accessible either.
So let me move on here to another question and ask you. In the complete mapping of the human genome has been criticized as not delivering on the promise of genomics by many people who have said, well, we've done it for about 10 years now, and it's so far, according to some critics, it hasn't delivered on its promises. What would you like to say to criticisms like that?
Well, I would have to say I'm one of the critics. I think that for every project, there's usually a diversity of opinions and a diversity of promises. I think that at least one report, however, has said that it exceeded expectations. So the Battelle report claimed that there was 140-fold return on investment. So for every dollar this United States society got $140 back. I wasn't part of that report. I'm not assessing it, but it's plausible. Mm-hmm. That a lot of genomics payoff is still in the future, in the same sense that if you tried to evaluate the transistor 10 years after the first transistor, say, gee, that's kind of disappointing. We have a transistor radio. While if you evaluated it 50 years later, like today, you'd say, yeah, that was pretty good return on investment. So I think the same things now that genomics is moving into the synthetic realm, we can expect more powerful and more rapid payback. Mm-hmm. But avoid making promises. I think that it's easier to look at the track record than it is to look at when and where.
Mm-hmm. Mm-hmm. Now, George, I had about over 50 questions submitted from the audience from this interview, and I've kind of integrated many of them in our conversation so far. But I'd like to ask you a couple, and because the time is advancing and we should be wrapping it up here within the next 6 or 7 minutes. So let me ask you a couple from the audience, and we'll close it with my two traditional final questions. So first, we have Szabolcs Kosa from Hungary, I think, who asks, how do you see the impact of advancing genomics on the average life expectancy worldwide in the next 30 to 40 years?
Right. So there's an interesting life expectancy trend, which is 170 years old now, where you get about a 1/4 improvement. So every year, life expectancy is extended by 3 months. Mm-hmm. Like is for every year, your life gets extended by 1 year. Then we
longevity is gap velocity.
Exactly. So I don't know whether that's going to arrive in the next in our lifetime. Mm-hmm. I really hope so. I think we should expect some pretty big breakthroughs, in part because within the next year or two, we're going to see the the publishing and utilization of dozens of people who live over 110 years and hundreds of people who live over 100 years, and what kind of protective DNA variants they might have that protects them against viruses, cancer, and senescence, other infectious agents. So I think that that will be incredibly potent. I think also we know quite a bit about senescence and cancer already, and if we work on synthetic biological reversal of those in human cells, we can get fairly rapid feedback as to because we now have such good control over the human genome and epigenome, that is to say, how the genome plays out.
Okay. The last audience question here would be this, and it comes with a quote from you in 2010 when you said, "They sequenced 93% of one genome. People have two genomes. They completely disregarded the issue of traits. It wasn't even from one person. The other 7% is so hard we still haven't done it." So first of all, for me, it was a total surprise that when they say the whole genome has been sequenced, it seems that only 93% of it has been sequenced. Would you mind talking a little bit more about that, and what's the last 7%? Are we still missing it, and why is it so hard to do that?
Right. Well, so those were a list of some of my critiques. Like I said, I'm a critique of the genome project that I did in, and have been since the beginning. I felt that there wasn't enough technology from the beginning, enough emphasis on quality, and integration with traits. So just knowing the ACs, Gs, and Ts without knowing how they vary from person to person, that should have been cooked in from the beginning. But anyway, we are where we are. The last 7%, some people just disrespect because it's kind of sour grapes argument because we can't sequence, it can't be that important. In many industries, we've seen like the automotive industry and the electronics industry, quality ends up being the dominant force in progress. If you go for quality, if you go for completion, like if you make silicon that's pure to 9, 10, or 11 nines, the 99.99999%, it results in better electronics, higher yields, better cost, and so forth. And I think the same thing is true for the genome. If we get so we can routinely produce complete genomes, that means 100% with less than one error per genome, it will end up being both cheaper and more medically useful.
Just so that I wrap my mind around this, why is that 7% so much harder than the other 93%?
Right. So it's repetitive, meaning that we're reading through. We kind of think like we're reading through a tunnel. We're reading little pieces of the genome at a time, and then we assemble it in the computer. And if a little piece we're looking at looks like another little piece somewhere else, then the computer gets confused. And so what we need is either longer reads or ways of segmenting the genome so that lots of little reads are all together as if they were a long read, a virtual long read, and so forth. So we need ways of making sure that we're looking at also that the inheritance from your mother and your father are nearly identical. And so it's easy to get confused as to which one you're on. So that repeats within a genome and between the mother and father's genome are confusing to the computer, but we're getting better at it. I'm fairly confident within the next year or two we will finally have a real 100% genome.
That's fantastic. Now, Dr. Church, what's the best place for people to find out more about you and your work and stay up to date with that?
Well, certainly there are plenty of news articles. I think the book, our website, has a news feed in it. So I think it's relatively easy. Just Google is probably the easiest way.
Okay. Now, the final question that I always ask of all the guests on my show is always the same, and that is, if you have a single message that the viewers and listeners of this show today can take away from this 1 hour interview with you today, what would you like that to be?
Well, that's a tough one. I think that the main thing is to stay engaged. We should be just as expert at science and technology, because that's what decision makers, and we're all decision makers, are making decisions about these days, much more so than ever before. So we should be just as expert about that as we are about everything else we read about in the news. And we should not assume that things will stay the way they are, or that inactivity is the right path. We need to consider risks and benefits of both inaction and various courses of action.
Mm-hmm. Dr. Church, thank you very much for being with us today.
Thank you.